Let's look at an example of sketching the graph of a function. So let's say our function in this case is f of x equals to 1 over 4 minus x squared. Now the first step is to find the domain. Well, for this rational function, the main thing is we cannot have any values which will make our denominator 0. So our domain in this case is from negative infinity to negative 2, union from negative 2 to 2, union from 2 to infinity. So the main thing is in the domain, we do not include negative 2 or positive 2. Now second, we find the x and y intercepts of the function. For our y-intercepts, remember you let x be 0 solve for y, so f of 0, when x is 0, we'd have 1 over 4 minus 0 squared, so that's 1/4. So our y-intercept is the point when x is 0, y is 1/4. Now for our x-intercepts, we let y be 0, or we set the function equal to 0, and solve for x. Now the thing is, if we set our function 1 over 4 minus x squared equals to 0, well, remember, for a fraction to be 0, the numerator has to be 0. And in this case, your numerator is always 1. So there is no solution to this equation, which means that there are no x-intercepts. So we look at the end behavior of the graph to see what happens as x goes to infinity and what happens when x goes to negative infinity. For both limits, as x gets really large, your denominator keeps getting larger and larger, but your numerator stays fixed at 1. So when that happens, the function is approaching 0 as x gets really, really large. Okay, next we got to find any of our vertical and horizontal asymptotes. Now remember, our vertical asymptotes for a rational function is when we can find values which make your denominator 0 but not your numerator. So in this case, our vertical asymptotes are the vertical lines x equals to negative 2 and x equals to 2. And for our horizontal asymptotes, we got that when we looked at the end behavior, and that gave us the vertical line, the horizontal line, y equals to 0, which is the x-axis. Now to find where is the graph increasing, decreasing, we look at our function, which is 1 over 4 minus x squared, and we got to find the derivative. Well, one way you could do this, if you want, you could use the quotient rule, or you could think of this as 4 minus x squared raised to the negative 1. So the derivative, using the chain rule, would be negative 1 times 4 minus x squared to the negative 2 times the derivative of the inside, which would be negative 2x, which would be 2x over the quantity 4 minus x squared squared. Now, when is the derivative either 0 or undefined? Well, it's undefined when x is negative 2 and when x is positive 2. And when is the derivative equal to 0? Well, that's when the numerator is 0, and that would be when x is 0. So those are our critical numbers. So we could plot those on the number line. And we got to look at the behavior to the left and to the right of these values. Well, to the left of negative 2, let's see if I plug in negative 3. Well, one thing, if you look at the derivative, it's 2x over 4 minus x squared, that quantity squared. So since the denominator is always being squared, that's always going to be non-negative. So we just got to see what will be the sign of the numerator. Well, if we plug in negative 3, it'll be negative. If we plugged in, let's say, negative 1, it'll still be negative. If we plug in 1, it'll be positive. And if we plug in, let's say, 3, it'll be positive again. So it's decreasing, then still decreasing, then increasing, and then increasing again. So the intervals from where it's increasing, it's from 0 to 2, union from 2 to infinity, and it's decreasing from negative infinity to negative 2, union from negative 2 to 0. Now the next step is to find your relative max and mins, and from the last part we saw that the derivative only changes sign from when you go from to the left of negative 2, or the left of 0 to the right of 0 is where it changes sign, and it goes from decreasing to increasing, so that means that we will have a relative minimum at x equals to 0, and the value of that relative minimum is, well, if we plug 0 into our function, we would get 1/4. Now the next step is to determine the concavity. Now to determine the concavity, we got to take the second derivative. So let's see, so the second derivative, that would be the bottom function, the 4 minus x squared times the derivative of the top, which is 2, minus the top function, 2x times the derivative of the bottom, which would be 2 times 4 minus x squared raised to the first, times the derivative of the inside, which is negative 2x, all over our denominator squared, which is the 4 minus x squared, now to the fourth. Well, let's see. We could factor from the numerator. Both of the terms have a 2 and a 4 minus x squared. So we could factor that out. Well, from the first term, there would still be a 4 minus x squared. And then, let's see, with the minus minus, that'll be plus. If I factored out that 2 times 4 minus x squared, so a 2's gone and the 4x squared's gone. So what you would be left with would be plus 4x. And that's all over 4 minus x squared raised to the fourth. Okay, now just make sure I did say 4x squared for that last term in the numerator. Okay, so that gives us 2 times 4 minus x squared times, combining those two terms, or the three terms inside the parentheses, we'd have what? 3x squared plus 4 all over 4 minus x squared raised to the fourth. And we could cancel one of the 4 minus x squared, so that would be 2 times 3x squared plus 4 all over the 4 minus x squared, now raised to the third. Now, we've got to see, when is the second derivative either 0 or undefined? Well, it would be undefined still at negative 2 and positive 2. Now, when is it equal to 0? That's when the numerator is 0. Well, if you look, well, we have 2 times 3x squared plus 4 in the numerator. Well, 2 is never 0, and the 3x squared plus 4, well, x squared is positive, times it by 3 will still be positive. Add 4 to it, it would be even more positive. So the numerator is actually never equal to 0. So all we got to look at is the behavior of the second derivative to the left and right and in between negative 2 and 2. Now, like I was saying, remember that the numerator of the second derivative is always positive, so we just got to see what about the sign of the denominator as when we plug in these different values. So for example, what if we plug in negative 3? Well, let's see, in the denominator, that would be 4 minus negative 3 squared, that will be 4 minus 9, so that will be negative 5 cubed. So the main thing is you will have a negative for the second derivative if you're to the left of negative 2. Now let's see, what if we plug in, let's say, 0? Well, if we plug in 0 into the second derivative, that would be positive. And now let's say if we plug in 3, that will be negative in the second derivative. So this is telling us that we'd be concave down from negative infinity to negative 2, and from 2 to infinity, and we're concave up between negative 2 and 2. Now, even though the concavity does change at negative 2 and 2, does not mean we have inflection points at those values because, as you recall from the very beginning, our domain does not even include negative 2 and 2. So it changes concavity at those values, but the graph does not even exist at those two values. So like I was saying, that there are no inflection points on the graph. Okay, what we're going to do next is put this all together and give a pretty good sketch of what the graph is like. Now let's put this all together and get a kind of a good rough sketch of the graph. Well, first thing I usually do is plot any of my points that I know, like the intercepts or the max, mins, or inflection points. In this case, the only point we have is actually the Y-intercept, which is also a relative min, which is 0, 1/4. Then I'd also graph my vertical and horizontal asymptotes. Well, we have a vertical asymptote at negative 2 and at positive 2, and we also have a horizontal asymptote, which is the x-axis. Now we know between negative 2 and 2, well, first it starts decreasing and then it's increasing, and it's concave up that whole time. So the graph will look something like that. And to the left of negative 2, well, for one thing, we know that as we go further and farther down to negative infinity, we'll be approaching the x-axis. But also we know that we're going to be, we'll be decreasing and concave down. So the graph will actually look like that to the left of negative 2. And to the right of positive 2, we know that it's increasing and that it's concave down, so it'll look like that. And that's a pretty good rough sketch of the graph.